MOSFET in class this morning. Are you ready? Yeah. We're looking at the MOSFET in the class this morning. So this is the symbol for the MOSFET that we use. Actually, maybe a second line here to show that there's a oxide junction. And when we plot the drain current ID versus VDS, we get a family of curves depending on how big the gate source voltage is. If the gate source voltage is less than the threshold voltage, we get no current at all, so the current is zero. So this is VGS is equal to VT. And then these are for VGS greater than VT, always increasing. So this is increasing overdrive voltage. And overdrive voltage, as you know, is defined as VGS minus VT. The larger you make the overall voltage, you get this. Now remember that this side of the characteristic is called the triode region. It's not a precise line, but this side of any characteristic, this is the triode region. And in the triode region, we have roughly changing resistance. So when the gate is only partially open, when the channel is partially open, you get a very high resistance. And as you increase the VGS, the channel opens up and you get lower and lower resistance. However, if you increase the drain source voltage excessively, a point is reached when the current doesn't increase anymore on a linear line, but levels off. And you can see that for any given value of VDS, as long as you're in the right-hand side, the current is fixed. This value of current, or this value of current, or this value of current. These are all constant currents. So if I plot these constant currents versus VGS, I will get a line that looks like this. This is ID, and this is VGS. And this is in the saturated state only. This is not true in the triode region. It's only in the saturated region. Or in the cutoff region too, you could say, because VGS less than VT is the cutoff region, which is just this flat line here, which everything is cut off. So this is the kind of characteristic we get. And the equation of this characteristic in the saturation region is given by ID, maybe I'll use black. It's given by ID is Kn over 2 VGS minus VT squared. And by the way, this, if you prefer, you can write it as V over voltage squared. I mean overdrive squared. So this is the equation. So the first part in your assignment, you're asked to look at a characteristic for this device and then find out what Kn is for this particular device. And that's not hard to do, as I said in class today. You can look at the characteristic, it'll look exactly like that, hopefully. You can select what, it changes with temperature, but you can select what temperature you think we are close to, and then you can find out what VT is. We discussed how to do that in class. Note that unless this is VGS now and this is ID. By the way, the characteristics are drawn with different X and Y scales. This is ID versus VDS. This is ID versus VGS. And this is only in the saturation region. This is not true in the triode region, because in the triode region, for the same VGS, you can have the ID depends on VDS. It's not a constant current. But in the saturation region, it's a constant current. So this is what we get. So you can find the threshold voltage by looking at this graph. Well, it's going to be here anyway, because until you reach VT, no current exists. So you can determine what VT is for the characteristic. And then you can just take any one point. Let's call it as ID1 and VD1, or VGS1, on your characteristic. Has anybody got a printout of the characteristic? Can I just take a look at that? I'll just... Yeah. Thank you. Yeah. If you look at it, here's the characteristic here. Okay? So from that graph looks identical to this one. You can take any other point. Thanks. Yeah. Or if you don't mind, I'll just hang on to it for a few more. No, I need the other one. Okay, this is good. So, by using some value ID1 and VGS1, once you know VT, you can determine what Kn is. So that was the first homework assignment. That was something you had to do at home. Okay, now the second part of the assignment was, remember that I'm going to move a little bit here now, Richie.
Yes, sir.
You see, it is asked, a circuit is given to you like this. This is what I screwed up in class today. All right, because I got confused myself. So this is VDD. This is connected right there. This is called RD. And it is asked of you, is this going to be in the active, saturation, or cutoff regions? Well, it could be cutoff. If you make VDD very small, then the voltage between gate and source becomes less than VT. And this is cutoff. That's easy to see. But now, could it be in the saturation region, or could it be in the triode region? Let's see. Now, for the saturation region, you need VDS to be large enough. In fact, VDS must be greater than or equal to the overdrive voltage, which is greater than or equal to VGS minus VT. So this is the condition for being in the saturation region. Okay, so only for large VDS, remember we said when the drain to source voltage becomes large, that's when the thing goes into saturation and escapes from the triode region. For some reason I was writing this as less than or equal to overdrive. The important thing is that VDS must be large to be in the saturation region. So obviously it must be bigger than something. So VDS. Now here you can see this is the gate, this is the source, this is the drain, and VGS is always exactly equal to VDS. So is this inequality true? Okay, it's true because VDS is equal to VGS, which means 0. If I subtract VDS from both sides, I get VDS minus VDS is 0. Should be greater than or equal to VGS minus VDS is 0 minus VT. Is this true or not? VT is a positive number. Is 0 greater than a negative number? Yes. So this circuit will always be in the saturation region because it is always true. This inequality is always true because of the way we have connected it. Right? So this is always in the saturation region. But it could be cut off too. So now if I start drawing, if I start increasing the VDD here, right, and I measure VGS and ID, how do I measure ID? How do I measure ID? Any idea? How do you measure current? Okay, well that is the answer I wanted. But my other question was, how do you measure a current? Usually with an ammeter. But we are not going to use an ammeter here. All right. So what we know is, if we just measure the voltage VDS, because we can measure that as a voltmeter, this voltage is VDD, which we can measure. VDD minus VDS divided by RD is going to be your ID. So you can then get this characteristic. You should be able to repeat this characteristic and get exactly what's on your data sheet to the millionth decimal place. Does that ever happen in any lab? Okay. So hopefully you're good to be good within 10%. Because again, anyway, you might be quite off. Because every MOSFET is different. Those are only typical characteristics they give you. It actually varies quite a bit. But hopefully you will find something like this, and you will be able to find the VT and ID. You will get another graph like this. So if I plot now ID versus VDS, I might get some other graph like that. And from this, using the same experiment that you did before, you should be able to determine Kn again. Now that Kn may or may not agree with the Kn you calculated from the data sheets. Hopefully it will agree, right? Did you do this experiment last year? No. Okay. So hopefully it will agree. Okay. So clear? Any questions so far? Now what is the next part of the experiment? Let me just see. So that is the pre-lab. Okay, using the circuit in figure 1, this is the circuit. Determine the threshold voltage VT. Measure the transconductance. Transconductance is essentially the this number here. and then construct a circuit of figure 2 and sketch VDS versus VGS. Okay, so now we do another circuit. We forget about this circuit, and now we build another circuit, which is the second part of your assignment. Of your lab. You're going to use this as an amplifier. Before you do that, you will build this circuit. You will apply a voltage, a signal voltage VGS on top of a bias voltage V, capital GS. Remember, all capital letters means the DC bias. This is the condition you need to operate, and then small letters means the signal. So the total voltage is small v capital GS. So all those graphs I had drawn here were always small I capital D. That means it's the full signal. Now we are looking at the small signal. Okay. Yes, you have a question?
No, this is question, sir.
All right. So now when you do that, this circuit satisfies two different conditions. As we saw before in class, it is always true that VDS is equal to VDD minus IDRD. This is Kirchhoff's voltage law and Ohm's law. These are just fundamental laws of circuits. So they always must be obeyed. So that's how it is. Right? So that's always true. So if I take my characteristic, now let me move over here. The circuit must satisfy these curves because these are the characteristics of the MOSFET. And on top of that, I can superpose my straight line. That is called the load line. This is called the load line. And the load line is basically the plot of this. Load line. So you superpose the load line on top of the characteristic, and wherever the intersection between the two is your operating point. So for example, if I have VGS equal to this value, then we must simultaneously satisfy two conditions. We must operate along this line, and we must also operate along the straight line, because we must always operate along the straight line. That is a fundamental constraint of Kirchhoff's laws. So there's only one intersection point, that must be our intersection point. All right? So that is how it is. Now, if you look at this graph, you will see that most of the time my intersection is in the active region. Or which is also called the saturation region. So here I am it's the constant current part. So this is, transistor is saturated. Transistor is saturated, remember it's on the constant current part. Transistor is saturated, transistor is saturated. How about here? Is the transistor saturated? Is it in the saturation region or is it in the triode region? It's in the triode region, right? So if I were to plot this, I would get something like this. In fact, let me plot it right on here. As I vary my VGS, okay, as I vary my VGS, so this is for a very low value of VGS, which is less than VT. No current is flowing. Larger VGS, there's a little bit of current. More VGS, there's more current. More VGS, there's more current, and so on. But I'm still operating on the active part of the saturation part. Saturation means active, as you know. In FETs, it's not like bipolar. But then at some point, if I make VGS even larger, then I will go into some other mode. And the ID will no longer be that value, but it will be less than that value. And in fact, the ID will never exceed VDD divided by RD, because it must be constrained to the load line. So what will happen is, if I do these plots, as I increase my VGS, I will follow this characteristic because I'm still saturated. But at some point, for a very large value of VGS, I will exit the saturation region, and I will settle down to some other value, which is not going to be bigger than VDD divided by RD. So you will trace out the characteristic ID versus VDS for saturation precisely, until, of course, your circuit is no longer in the saturation region, like at this point. And then of course, the ID that you will get will be less than that ID. So you will deviate from the ID versus VDS curve that you had been given in the data sheet. Okay, is this clear? Someone asked me this question, why don't you, young lady asked me in class today, that why is this not following that? And that's the reason. After some time, we are no longer in the saturation. Okay, so now let's do one thing. Let's first, in order to find out, we want to find out, maybe we would like to find out the voltage gain of this circuit. Voltage gain of this circuit is equal to VDS divided by VGS. And these are all small signals, so I'm writing small letters. I hope you know the difference between small and large signal, if not ask your TAs. At least you hear remembering about it. I mean, remember hearing about it, right? Alright, so this is VDS. And what we can do in order to, first let's find the current gain. First find current gain. Okay, current gain will be, and maybe I will say in saturation region. Saturation or active. Saturation means active. Because when a MOSFET is saturated, it's active. When a bipolar transistor is saturated, it's saturated. It's not active. It's different terminology. So first find current gain. So what I will do is I'll find ID versus divided by VDS. And to do that, what do? I can take current gain, let's call it as AI, is equal to the rate of change of current with rate of change of VGS, evaluated at VGS is equal to the Poisson point. Okay. So if I bias means the steady state voltage, if I apply this voltage, say equal to, I'll use a different color. Suppose I bias the circuit at this point. So this is now my bias point. Let's call it as V, capital VGS. This is my bias point, or some people call it the quiescent point. So this is my operating point. So what is the slope of this curve? The slope of this curve will be a small change in VG will make us to the small change in ID is essentially the slope of that curve. Because as you know from calculus, the meaning of dID by dVG S is the same as delta of ID, small change in ID divided by delta of VGS, of course, as the limit VGS goes to 0, because that's the official definition of a derivative. But engineering wise, small change in ID divided by small change in VGS is basically the derivative. Alright, so you can find out the derivative at this point, and from that you can figure out what the gain is. And that's not hard to do, by the way. What is the gain now? We know that ID, what is dID by dVGS? Can somebody give me an answer? dID by dVGS. This is the expression for ID. Can you take the derivative? What's the derivative of that? Should we say that it is Kn times VGS minus VT? Is this correct? Or am I wrong? I think that's right, but you can check it. So that really gives you the gain, and the gain depends on what operating point you have. If I change the operating point on the DC bias, if I operate at that point instead of that point, I'll have a different gain. Alright? But basically this is the equation for the gain, Kn VGS minus VT. So you can then calculate the gain for your circuit depending on where you're operating on the characteristic. Okay? I don't think you're asked to actually do that. You're asked to do that experimentally, but you can also give it analytically. I mean, you can calculate it. So that's how the gain is. But this is not the voltage gain. We haven't yet told the whole story. So if this is the current gain, then what is the voltage gain? Now you will see that VDS is equal to, what is VDS equal to? VDD minus ID RD is equal to VDS. So if I write this as small signal, what is the small signal component of VDD? It's a constant voltage. So it has no small signal component. Minus ID RD is equal to VDS. Okay. So essentially, VDS, the small signal component, you can ignore the DC part, is basically minus ID RD. And so if we know the current gain is this, then therefore delta VDS divided by delta VGS simply becomes minus RD times AI. Okay, so essentially, that is the voltage gain. Now, I think this is capital R. Sorry. All right. One of the questions that you have to answer is, what happens when RD changes? Can you answer that question? How does the value of RD affect the gain? Can you answer it? Hopefully you can. Right? And the TAs will obviously ask you this and you will be required to answer it. Right? So what else is left in the thing? So what you will find is here, so if you're operating say at this bias point, let's say there's another characteristic through it. And so this, let me plot my, sorry, not this one. Let's say over here. So essentially what I will find is, I'll get another characteristic. If this is the current characteristic, I will get a voltage gain characteristic that will look like this. Anyway, let me actually show you the large signal picture of the. So, if my ID versus VDS looks something like this, this is all capital, all the large signal. I follow the idealistic characteristic, and at some point I move away. And then if I plot VDS, which is simply VDD minus IDRD, you will see that as ID increases, VDS decreases. So initially you will have VDD, because when ID is 0, then VDS will be equal to VDD. And when ID becomes larger and larger, you will start dropping like this. Some point around here, you will hit the point at which your thing goes into the triode region, because now you're entering this part of the characteristic, and then you will level off like this. Something like that. So that's in the triode region. So this is triode, this is saturated, and this is cutoff. So now if you bias your signals, let's say this is your VGS, this is time, I'm drawing a graph like this, going in that direction, time is increasing here. If this is my small signal on it, then at this operating point, the output voltage that I will get will be it will have a much bigger amplitude. So if this amplitude is, let's call it V1, this amplitude will be AV times V1. Notice also that this is an inverting amplifier because there's a minus sign here. We had VDS is equal to minus AI times RD. We saw that there's a minus sign because as you increase this voltage, the output voltage decreases. So you have a minus sign there. So this is how you will calculate this. And of course, the region that is open to you for doing the amplification is this. Only within this active region do you get amplification. If you're operating here, you don't get amplification. If you're operating here, you have zero current, you don't get amplification. Okay, so it's in this region that you get amplification. I think that answers more or less all the questions. Can I just double check here? Yeah, so that they've asked you to measure the maximum peak to peak amplitude you can get. before your amplifier stops behaving like an amplifier. So if I make this signal too large, then you will see that it will exceed this range, and then it will clip. Here it won't go, and then on this direction it will clip somewhere here. Can't go above VDD. And so it will be that range. So they've asked you how big can you make this range. So I think that answers all the questions here. They've also asked you what happens if you change VDD in this graph. And I'm not going to answer that question. I'm going to leave it to you. But the hint is you could use the load line. If I increase VDD, this value is VDD over RD, and this value is VDD. Okay, so what happens if I change VDD? This point will go here. The characteristics move. You can try to answer the question based on that. I'll leave that completely to you. Okay, so I think I've answered almost all the lab questions, and I think this is where I'm going to stop. Are there any questions from the TAs or yes?
Will you write a report?
No. What you have to do? I forgot to mention. Everybody. I don't know if I mentioned this. It was on the website, but you have to have your own lab notebook. Do you have your own lab notebook? Okay. So have your own lab notebook. You must bring the same lab notebook to class every week. You take all your readings and everything in that notebook in neat lettering. There's no written report. You'll get marked at the end of this lab session, and you forget about it. Well, you don't forget about it. You don't have to do any further work. So that is how we do it. Okay? But you have to have your lab notebook. Maybe we should send an email out today that everybody has to have their lab notebook. Yeah, I was going to mention it. Oh, one other thing that we have to say is about safety regulations. You have the TA's names on the website. This is Shomi and this is Yichi. Shomi. Yeah. So really about safety, the only thing you really have to worry in this lab about safety is there are some 110 volt contacts. So don't put your fingers near the plugs. Make sure the plugs are properly inserted in the units. So you, in third year now, you should know where the power comes into your computers, your screens, or even your breadboard. So be careful about that. Now, there's a possibility that something is not grounded properly and you may get a shock when you touch something. Okay, bring that immediately to the attention of the TA. Now, if there's a fire and you have to exit, by the way, these are new rules that came through the university, so we have to tell you. It's a good idea, it's not a bad idea. Then there are exit signs outside and there'll be an alarm. Just follow the usual procedures to exit this building. Okay, so I think we have to say that. Okay, that's it. Any other questions? Okay, so I then wish you good luck with the lab. I'll make a round later, but right now you're on your own. Are you okay with what I explained?